Hello everyone and welcome back. The video this time around will be probably much shorter than usual, but I do believe that the result that we'll get today is a bit too beautiful to not to have its own video. So here I am and this is what we'll be doing today. So if you're unfamiliar with what binomial coefficients mean, it's basically the number that accompanies the a and b when you expand a binomial. So suppose you have next binomial over here. I'm going to call it a plus b, and you raise it to some power n. All right. So for now, let's just take it as 2. So we know what the expansion of this is. This is a square plus 2ab plus b square. All right. And we can take a plus b the whole cube, and the expansion of that would be a cube plus 3a square b plus 3ab square plus b cube, and so on and so forth. But is there a way that we can generalize this? Well, fortunately for us, Newton has already done that for us. And if you are interested, you can look at an inductive proof of it. It's not too complicated, it's just for doing a proof of induction. So if you're interested in that, you can look at that. But here, if you just take the expression for granted, and that expression is actually a plus b raised to n is equal to sigma, so that is we are summing up over all the quantities that we have. Sigma I is equal to 0 to n of n ci into a raised to n minus I. You might see this done with r. In fact, even I do it with r. I have no idea why I chose I over here. But yeah, we can, so n minus I into b raised to I. Now this over here is actually the symbol that is used for combination. I'll get to that in a minute. And this is a raised to n minus I, and this is b raised to I. So if we just quickly cross check this for n is equal to 2, we see that you have to sum up over 3 terms because you have 0, I is equal to 0, 1 and 2. And then there will be nc0, nc1, I mean n over here is 2, so that will be 2c0, 2c1 and 2c2. And we'll have a square, a, and then a raised to 0. So I mean what the expression we'll eventually get is basically a square plus 2ab plus b square. So there's that. But what does this term NCI actually mean? Now, I'm assuming that if you're familiar with the binomial theorem, you already know what this term means. But those of you who aren't, NCI or NCR is basically the number of ways you can choose odd number of objects out of n number of things. So suppose you have like 3 pens just lying around over here, and you want to choose any 2 pens out of these. So I'm just going to call these pens A, B, and C. And so what happens is the number of ways that, suppose I want to choose one pen, right? And I have 3 pens, so I can choose either pen A, I can choose either pen B, I can choose either pen C. So what we can say is 3C1 is equal to 3. Similarly, if I wanted to choose any 2 pens at a time, what I could write is 3C2. So let's look at how many ways I can do that, right? So I can choose either A and C, I can choose either B and C, or I can choose either A and B. So again, we have 3 pens. I mean 3 ways we can do that. But what if I wanted to choose 3 pens and what if I wanted to choose all 3 pens, right? And there's only one way of doing it. So that would be just 1. So this is just an intuitive understanding of what combinations mean. And just to recap, because if you're watching this video, you definitely know what combinations are. But I just thought I'd go over it. But more generally speaking, the formula for a combination can actually be written in terms of factorials. Alright. So that is actually equal to n factorial by n minus r factorial and r factorial. And of course, factorial is the multiplication of all numbers from n till a 1 going backwards. So that was that, and it turns out that these are actually the combination of is actually what we call the binomial coefficients over here. So NCI over here is the binomial coefficient of this term over here, these two terms. Alright, so that is what we are looking at. I mean, this is what you're interested in, that is just secondary. So what I want to actually do over here is to get the result. What we want to do is we want to try and isolate just this term, yeah? And that can occur when both A and B are 1. So if we take the special condition in which both A is equal to B is equal to 1, what we get is 1 plus 1 raised to n is actually equal to, so let's just write let's write all the terms to be more clear in what we'll get. NC0 into 1 raised to n minus 0, alright? But 1 raised to n number is just 1, and similarly b raised to 0, and that's just, I mean 1 raised to 0, and that's 1 as well. So what we'll get is just nc0, then we'll get nc1 plus nc2, and so on and so forth. You can also cross check the fact that this will again be 1 over here, so we'll just get the binomial coefficients, and so on and so forth till ncn. So what we actually end up getting is nc0 plus ncn and so on and so forth is equal to 2 raised to n. And this was what this video was about. I know it seems like a really elementary proof, but just, I mean, it's baffling to think how an exponent figures into all of these expressions that are basically factorials, yeah? Really just the fact that how elegant this expression was what made me want to make this video, even though it's actually quite simple according to me. So let's just have quickly cross check this to see if it's correct or not, right? So we'll take the same example of 3 that we had over here, right? So let's take 3c0 plus 3c1 plus 3c2 plus 3c3. Now 3c0 is actually 1 because you, when you don't choose anything, there's just one way of not doing that, right? I mean, if you're asked to choose 0 objects out of 3, there's only one way you can do it, by not choosing anything. So that is just 1. Then you have plus 3, as we just saw earlier, plus 3 plus 1, and what you get is 8, which is nothing but 2 cubes, so the formula obviously works. But in addition to this, if you might be wondering where exactly might this formula crop up here, and it turns out literally everywhere, because choosing things, because the sum of choosing things is actually very useful in a lot of places. So if you have actually had an elementary course on set theory, which I'm assuming that you have had, so suppose in set A it has n elements, yeah. So this is a set A, so it's like 1, 2, 3, so on and so forth. This set has n elements. So it's often stated that the power set, that is the set of A containing all these subsets that can be created from set A, contains 2 raised to n elements. But why is that the case? That is nothing but and the reason for that is nothing but what we just saw here, because suppose I can write this as phi, that is the null set. I can write this as 1, I can write this as 2, I'm assuming that this is this set that we just had, and so on and so forth, containing all the subsets. So this actually involves you picking no elements at a time, then just 1 element at a time out of all the n elements that you have, then picking 2 elements at a time out of 2 elements at a time out of the n elements that you have, and so on and so forth until you have to pick a set where you pick all the n elements at a time out of the n elements that you have. And that is nothing but choosing things, yeah? So again, our trusty combination formula comes into hand, and we can say that the number of elements in the power set is actually 2 raised to n. And the same thing goes with the number of relations that can be made from a cross product, yeah, because we know that the cross product will have m cross n, m into n elements of any two sets when you do a cross product of any two sets, and we see that this all the relations that can be made are basically subsets of the cross product. So the or the Cartesian product, my bad. So the number of relations that can be defined from set A to B is nothing but 2 raised to mn. And you can find infinitely many more applications of this simple formula. And personally, that's what I really like about it. It's so elegant, it's so simple. And thank you for watching. I think that will be it. And see you next time.